So the topic in my chapter 16 and your 17.4 to 17.7 is both solubility and complex ion equilibrium. So I warned you guys earlier that we're not giving up on equilibrium. We introduced equilibrium, chemical equilibrium, and then we went into acids and bases and used it again. Now we're going into solubility and complex ions, and we're going to use it again. Equilibrium is a big part of whatever we do. So let's move on. This is a fairly short chapter, but I need to dwell on the slides a little longer than normal. So when we write an equilibrium expression, let me back up. In the first semester, we learned about precipitations, reactions that produced a solid or precipitate. And at that time, we looked at solubility in terms of black and white. Wait a minute. I don't see myself. I guess that's all right. So we discussed solubility in terms of black and white. It's either soluble or it's not soluble. But as a matter of fact, there's a gray area between soluble and insoluble. There are very few compounds that are absolutely insoluble. Zero amount of the solid goes into solution ever. Those are rare. Most of the solubility questions are in the gray area in between. And you may have some compounds that are just very slightly soluble, and then some that are more soluble. So we're going to quantify that in this chapter. This example has bismuth sulfide. Which is a solid, and we're going to put it in aqueous solution. And by the way, we're only going to talk about aqueous solubility from now on. So how many ions would this produce? Well, this is a 2- charge. This is a 3+ charge. We can tell that from the coefficients. So when this breaks apart and actually goes into solution, we're going to have 2 bismuth ions and skip over this bright spot. Or I can put it up here. And 3 sulfides ions. And these are in aqueous solution. Okay. Now we know how to write an equilibrium expression for this. We say the K for this one would be products. So bismuth 3+ ion squared, right, times sulfur 2- ion cubed. All right. And we did learn initially in equilibrium that the terms that are left out of the expression are either pure liquids or solids. So this solid does not go in here at all. In fact, we ought to move this K up here. That's why it has a subscript of SP. SP means solubility product. And this is the format for every solubility expression, equilibrium expression. It's only the product of the ions that are produced when the solid goes into solution. Okay. Let's see. I want to be sure I'm not missing something. Right. Like any equilibrium expression, this is dependent upon temperature. So if we change the temperature, we get a different solubility product. And this solubility product, this K value, is constant under constant temperature situations. But the flip side of the coin is solubility. In other words, solubility is an expression of how much. Solubility is the moles or the mass, usually, the mass that goes into a solution, say 1 liter. That is analogous to an equilibrium position. You can have a greater amount solubility of the substance going into solution, but at the same temperature, the K will always be constant. All right, so let's move ahead. So this is just a check to see if it sunk in. If we compare several salts at a given temperature, and they have different KSPs or solubility product values, does that always mean a higher solubility? And in fact, it does not. The reason for that is mathematical as well as physical, because you have these powers here that have to be taken into account. This value could be wildly different than solubility. In other words, you can have a KSP of one salt that's very small, but it'll have a high solubility, and vice versa. Yes, solubility is usually expressed as mass per unit volume or moles per unit volume. It could be in molarity, it could be in grams per liter or grams per milliliter. That varies. That's what solubility expression is. And the KSP incorporates these powers. Just like any equilibrium expression, you have these powers, and as a consequence, we don't assign any units to the K value, whereas the solubility will have units associated with it. Now we can use this and some other information to determine the solubility, and that's one of the things we're going to do in a few minutes. They are related, but they're not the same. That last line is kind of getting ahead of things. I guess I could explain. Yeah, that's okay. Using this as an example, we want to know what's the solubility of this compound. So it would be so many grams of the compound per liter, say. Let's make it easier than that. Let's make it moles per liter. Let's make it molar solubility, moles per liter. Okay. If we have so many moles of this one going into solution, say we have 1 mole of that. So how many moles of this do you have? You have 2. So if the solubility here is given a symbol S for the solubility of that compound, then for every one of these, you get 2 of those. So that means this value would be 2S, right? Because you get 2 for 1. And this one, solubility would be so many moles of this compound per liter, you get 3 S's. Okay? Because for every one of those, you get 3 of these. So now, 2S squared would be 4S squared times 3 cubed would be 3 times 3 is 9 times 3 is 27. S cubed. So 4 times 27, I don't trust myself on that one. 108. So this would be 108 S to the 5th power. So the solubility and the solubility product are related by this method, where if we say the solubility is so many moles per liter is equal to S, then this relationship says that this value would be 2S and this value would be 3S, and we calculate D. So that relationship holds depending on the balanced equation. Okay, so calculate the solubility of silver chloride if KSP is 1.6 times 10 to the minus 10. All right, so let's make room. Yeah, let's just do it like this. Okay, so how would we write the solubility expression for silver chloride? Well, first you have to write silver chloride correctly. And then it's in equilibrium with silver ions and chloride ions. Okay, so the KSP would simply be silver times chloride. Because the coefficients are 1, each one. We're given the value for KSP as 1.6 times 10 to the minus 10. Okay? And there we go, and there we go. Okay, that's as far as we've gotten on the board. Next, okay, we jumped over. Let's use the ICE table to prove where this expression came from right here. All right. So let me get that out of the way. There we go. So an ICE table here would be, I'm going to move it down here to get out of the way of those things. ICE here. Okay. This one has no concentration, so it's not even going to have a value there. But in the beginning, actually, we have 0. Before any of it goes into solution, we have 0 silver, 0 chloride. The change then is going to be, for every one of these, you get 1 and 1. So we're going to have an X here and an X here added. So that's X and that's X. So now this would be substituting X here and X here, and that would be equal to X squared, correct? Okay. So what's X? X is the square root of 1.6 times 10 to the minus 10. Oh, it's already given for us. 1.3 times 10 to the minus 5. Okay, and that's molar. All right, so what does X mean? In this context, if X is that, it's also equal to this. So the molar solubility of silver chloride is 1.3 times 10 to the minus 5th molar because of the 1-to-1 relationship of X. Okay? Or this might even make more sense. If we say the solubility of this is some value S, that means this is going to produce an S and this is going to produce an S. So we could change these to S. Right? We're going to get an S here, we're going to get an S there. So that's S, and this would be S and S, solubility. This would be S, and this would be S. That way, we know that when we get to the bottom of our calculations and S equals that, we know that is the solubility. So that's where that expression, that X times X came from, is from the ICE table. So let's try a different one. I'm going to set it up a little different so I don't have to jump over these boxes. Okay. So let's set it up over here. So we've got silver phosphate. Silver and phosphate. Well, phosphate is a 3-, silver is a 1+, right? So we have to have a 3 here. And that's a solid. So that's going to break up into 3 silvers and 1 phosphate. Okay, and these are aqueous. Okay. Let's see, I can get rid of that. All right. So our KSP for this reaction is going to be silver cubed, right? Because the coefficient. And then phosphate to the first power. Like that. And we're given 1.8 times 10 to the minus 18. There we go. Okay, now let's do our ice table. Okay, so if the solubility here is going to be represented by S. Okay, so that means this starts off at 0, and the change is going to add 3 S's. And they're going to add 1 S here, because that's 1, this is 3 of them, and this is 1 of them. All right, so we have a 3S and an S in this expression. Cubed and a 1S. First power. There we go. And that's equal to 1.8 times 10 to the minus 18. Now we just need to resolve this and solve for S. All right, 3 cubed is 27 times 1, and then 3 S cubed and S to the first power is S to the 4th power is equal to 1.8 times 10 to the minus 18. Okay, so S to the 4th is equal to this number divided by 27. So let me do that. 1.8 exponent 18 minus divided by 27, and this is 6.67 times 10 to the minus 20, and S is going to be the 4th root of 6.67 times 10 to the minus 20. Now, I don't know if you know how to work the larger than square roots in your calculator, or cube roots. Sometimes they have cubes also. But you need to learn how to do that. Otherwise, your only other option is to do logarithm conversions. But if you can do the 4th root, actually, what is the 4th root? If we say the 4th root of X, we actually mean X to the minus 4 power. I believe. Isn't that right? Let me test it. Let's see. 2 times 2, 4, 8, 16. So 16 would be the 4th root of 2. And let me see if I take that to the minus 4 power. That didn't work. Hold on a second. Enter. No, not minus 4. Excuse me. 1/4 power. That's what that means. So 0.25 and then hit this one like that. Yes. Okay. So you could do it that way. Maybe your calculator doesn't have the X root function. But if you can do X to some power, then you can change the 4 root here to 1/4. And that will work. That's the way I have to do it in my calculator. Okay, so let's take this value here and do the 1/4 power of that one. 6.67 exponent minus 20, and then 1/4 power. 1 equals 1.61 times 10 to the minus 5 molar solubility. Okay, now let me see. Is it worked out? 1.6, 10 to the minus 5. Okay, so it worked. That's how you determine, that's how you calculate the solubility of a sparingly soluble salt if you already know the KSP. All right. So, how does the solubility of silver chloride in water compare to that of silver chloride in an acidic solution made by adding nitric acid to the solution? Okay, here, this is a discussion of the common ion effect. So if you're going to talk about silver chloride going into solution, to produce silver ions plus chloride ions, and you're going to add nitric acid to it, right? Right, and these are going to, nitric acid is a strong acid, so it's going to completely into solution like this and produce these ions. What effect will these have on that solubility? Well, what could hydrogen react with? Well, it could react with chloride, but it won't, because hydrochloric acid is strong. It's completely dissociated. They don't care about each other. This is a very weak base. It doesn't want that proton. Okay, so that's out. How about this one? Silver and nitrate. How do they react? Well, if you look it up in your chart, the solubility chart, you'll find that silver nitrate is completely soluble. So they're not going to associate either. There are no common ions in here to affect this equilibrium. Nitric acid will have no effect whatsoever on the solubility of silver chloride in aqueous solution. Okay, so there's your, that's what I just showed you. And when you add them together, what do you get? Well, you still get free ions, right? So the solubility is going to be the same no matter what. There are no common ions between silver chloride and nitric acid. Okay. How about silver phosphate in water? And you make your solution with nitric acid. Okay. Let's take this one. Let's go over here. So silver phosphate solid produces 3 silvers plus 1 phosphate. Okay. Now when you add nitric acid to it, what does it do? It completely dissociates just like before. Nitric acid. Okay. What possible reactions could we have here? Well, the nitrate and the silver, they're not going to do anything. But phosphate and hydrogen ions. What kind of reaction could you get from those? Remember when we were talking about acids and bases, we had phosphoric acid is in equilibrium with this ion, like that. And then the next one, PO4 minus, is in equilibrium with this one. And then this one, finally, is in equilibrium with this one. Okay. Notice that this has a dissociation constant. This one has a smaller one. And this one has even a smaller one. Right? So you're not going to get much over here because the K value is very small. So what that means is if you've got hydrogens available, that phosphate is going to pick them up and it's going to go right over here. And then if you still got some more hydrogens available, this one's going to pick them up and go over here. And since this is the conjugate base of a weak acid, it's a strong base. These are all strong bases. They're going to go after any hydrogens that are available. So it'll go bam, 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 all the way back up to here. So what that does is it picks up this one, combines with that one, and further hydrogens can combine with the subsequent polyatomic ions. So what you're going to do is by adding hydrogens here, depending on how many you add, you're going to consume phosphate quickly and completely. What does that mean? Based on Le Chatelier's principle, you're going to drive this reaction to the right. So you will increase the solubility of silver phosphate by acidifying the solution. And this is the way it looks in, there we go. Silver phosphate becomes more soluble in acidic solution because the phosphate ion is a strong base, driving the reaction, driving the solubility reaction to the right, just like we said here. All right. But how does the KSP of silver phosphate in water compare to that of silver phosphate in acidic solutions made by adding that acid? The KSP is the same. We drive the reaction to the right, just like we did with any of our Le Chatelier reactions. We drive the reaction to the right, but that's only an equilibrium position change. It doesn't change the K. The K is going to be the same no matter what we do to that solution, as long as the temperature is constant. All right. So let's make room for some more stuff. Calculate the solubility of silver chloride in these various solutions. All right. So silver chloride, let's just put it up here again for reference. Silver and chloride. Okay. So our first choice, A, is, well, let me put the KSP up here too. KSP equals 1.6 times 10 to the minus 10. I think that's what I saw. Yep. 100 milliliters of 4.00 times 10 to the minus third molar calcium chloride. Okay. Calcium chloride is completely soluble in water. So you're going to have calcium ions and chloride ions. Notice if this dissociates completely into calcium and chloride ions, right, in aqueous solution, this ion is common to that reaction. Okay? Since it's common, if there are already chloride ions in solution, when you try to put silver chloride into it, you've already got some of these here. So while you don't have any silver there, and the equilibrium will shift to the right a little bit, it won't shift as much as it would with pure water. So the solubility should, qualitatively speaking, go down because of that common ion effect, right? Here's the calculation, right? If we use that as our, let's see, well, I drew this in the middle. I'm going to take a chance and hope it works. Okay, so if the solubility is a certain amount, then we need initial change equilibrium, right? So what's the initial concentration of silver? 0, right? What's the initial concentration of chloride? Well, it's this concentration times 2, because this is the concentration of the compound, but we get 2 for 1. So this one should be 8 times 10 to the minus 3 molar. Okay, we're still going to go this way, right? So some of this, one of these is going to be 1 to 1, and this one is going to be also plus X. Okay, so I'm going to skip over that and come down here. This is going to be, well, I'll tell you what. I should be using S here, solubility. There we go. So this is going to be S, and this is going to be 8.00 times 10 to the minus 3 plus S. Okay? Now, if we put that in our expression for the KSP, this is 1, that's 1, so it's just going to be this one times that one equals that KSP. So 1.6 times 10 to the minus 10 equals S times 8 times 10 to the minus 3 plus S. Okay? Now, what we're saying, we're going to use the approximation. Since this is very insoluble, notice that a very small number, we're going to say that this one is so small that we can ignore it. So we're going to say approximately this. It's this one times this one. So it's 8.00 times 10 to the minus 3 S equals this one. So S is just this one divided by that one. There we go. So not trusting myself to do this in my head, I'm going to type it out. Oops. Exponent 10. There we go. Divided by 8 times 10 to the minus 3. There we go. 2 times 10 to the minus 8. Molar solubility. I'm just making a point here. The problem said we had 100 milliliters of this. It doesn't matter. We're talking about concentration, not total amounts. So we determined what was the solubility before, or is that on the next page? No, it's not. Okay, let's go back. I'm going to scoot back here and see, did we determine the solubility? Yes. In water, the solubility of silver chloride is 1.6 times 10 to the minus 5. Okay, so for comparison, we find that the solubility of silver chloride in this solution has decreased by 3 orders of magnitude. But the solubility product hasn't changed. It's just simply the fact that we have a common ion there that's preventing more of the silver chloride going into solution. All right, so what do we have on the next page? Silver chloride and calcium nitrate. Well, if this were calcium nitrate, oops, wrong place. All right. There we go. Then we would get 1 calcium and 2 nitrates. All right. Okay. Is that going to have an impact on the solubility here? No. Calcium chloride, right? Calcium ions and chloride ions, no change. Nitrate ions and silver, no change. Calcium nitrate will have no impact on the solubility whatsoever. There's no common ion. So we're back to, now why is that 1.3? We calculated that to be 1.6 in the previous slide. Unless I read it wrong. Hold on a second. Oh, I was looking at the wrong one. 1.3 times 10 to the minus 5. My mistake. There we go. So this should be 1.3. There we go. It's still over 3 orders of magnitude difference. Oh, excuse me. Yeah, 3 orders of magnitude. 1,000 times less soluble if there's that common ion. Now this will change. This value, the solubility will change depending on the concentration of that calcium chloride. If we increase the concentration of calcium chloride, the solubility of silver chloride will decrease. This will be a much smaller number. If we make this a smaller concentration, then the solubility of silver chloride will increase. Okay. Let's see. I'm going to leave that right there just for a second. I may need it to discuss. So we can calculate Q for any reaction. If we have this one, and we know that there are ions already in solution, I'd say we have so much silver, so much chloride in solution, we can calculate a Q value. We just set it up like we did with our previous equilibrium expressions and compare that to the KSP. Okay? If the Q is greater than the KSP, right? If we have a value here and a value here, and we calculate the Q and it's greater than that value, right? Because KSP is equal to this expression. If we calculate Q and the Q is bigger than that, that means we've got too much of these, too much of those, and we're going to get a precipitation. Some of it will drop out of solution, right? If that's the case, then what's left is a little bit of solid on the bottom, silver chloride, plus a saturated solution above. And if the Q is less than KSP, that means we don't have enough of these. And the shift will be to the right. Or we can look at it another way. Since we're given concentrations of these two, that means that we've got them in solution and we want to know, will they form a precipitate? And if Q is greater than KSP, yes, they will form a precipitate. Q is less than KSP, no, they won't. Okay, there we go. There we go. All right. This leads us to a wet chemistry technique that's been used for decades, if not centuries, is the selective precipitation of metal ions from solution. If you get a mixture of metal ions in a solution with some counter ion that is completely makes the metals completely soluble, then one way to retrieve those metals selectively is to choose the anion correctly and the reaction conditions correctly so that we can selectively precipitate the metal as we wish. Okay. We have to choose the reagent so that we get an anion that will form a precipitate with only one or a few of the metal ions. Sometimes we have to, we have a mixture. Sometimes we have to add something to the mixture so that we separate out several ions. And we leave some of them in solution. Right? This is in solution. This is precipitate. And then we take, these have been precipitated. These have not. So we add something else to them and try to selectively precipitate those. So what do you do with these over here? Well, you may have to redissolve them and try a different precipitation. So it can get kind of unwieldy, but there are recipes and there are flow charts that help you decide what to do first and what follows that to give you the most efficient separation. And that's what I'm going to show you in just a minute. So in this example, we have barium and silver ions in solution. We know that that's all there is. So if we add hydrochloric acid, we will form a precipitate with the silver chloride. It will drop out of solution, and barium chloride is soluble. Now, if we used another source of chloride, we could effectively remove silver as silver chloride. But if we use sodium chloride, then we're contaminating our solution with sodium ions. Right? And then we've got to separate those from the barium. So that's another factor to consider. Okay, let's say we have copper 2+, mercury 2+, nickel 2+, manganese 2+, and we use hydrogen sulfide. All right. So hydrogen sulfide, excuse me. If we put hydrogen sulfide in solution, right, it's going to set up an equilibrium with 2 hydrogens and 1 sulfide in solution. Okay. If we want to precipitate one of those or more of those ions from solution, what we need to do is guarantee that there's not much sulfide in solution to react with, say, mercury and copper. Mercury 2 sulfide and copper 2 sulfide are very, very insoluble. They have very low solubility products. So we don't want a lot of this in there. We just want enough to precipitate the mercury and the copper, but not enough to drive the Q of the nickel and the manganese sulfides above their KSP. So we keep this very low in our first step. So that means it needs to be in acidic solution. This needs to be acidic or low concentration. There we go. As it turns out, this tells us what this relationship, remember, treat this like an acid, right? This will go, excuse me, I went too far. We only need one hydrogen. And like that. So the K for this one is 1 times 10 to the minus 7. And then we take this one and extract another proton. And that gives us the sulfide. And this K, this is 1, this is 2. This K is 1.2 times 10 to the minus 13. Okay? So overall, the K, if we add these together, we get that previous equation that I had written up here. And the overall, 1 plus 2, actually 1 times 2, isn't it? 1 times 2 is equal to 1.2 times 10 to the minus 20. What that means is this is very insoluble. It produces only a little bit. And this is the species that we want to react with the mercury and copper right here. So this is the overall equilibrium. And what we need to do is choose our conditions so that we have just a little bit of this. I got that explanation backwards. Copper sulfide and mercury sulfide are more soluble than nickel and manganese sulfide. So when this goes into solution, this is going to react with mercury. Let's see, is that right? Oh, I did have it right. Right? Mercury and copper sulfides are very insoluble. So you want this one just as is in solution to produce just a tiny amount of that, and it will precipitate mercury and copper. And then if you add hydroxyls to it, what does hydroxyl do? Right? It produces 2 waters and drives the reaction this way, producing a lot more of that. Now, after we've removed this as a precipitate, and when that precipitates, you filter it. Just pour it through a filter and extract the precipitate. Then you go back and add the hydroxyl. And the hydroxyl then takes this hydrogen sulfide, drives the reaction this way, and produces a lot more of that. Now, when we have more of this, the Q for nickel and manganese as products increases. And it increases to the point where it exceeds the solubility product of the nickel and manganese. And I think that's on the next slide. Yeah. So this is a flow chart describing H2S. Now, what we often do, though, is we add hydrogen. For the first step, we add acid and decrease the pH to around 2. If we add this, that's going to go this way and only leave a tiny amount of this one. So that's when we pick up copper and mercury. And then when we add base and neutralize the added acid, we drive the reaction back this way and produce more sulfide, and then the sulfide picks up the manganese and the nickel. Okay, I hope I didn't confuse you too much. All right, so here's a selective precipitation chart that works on the same principle, except the first step in this one, and we've got this big collection of metal ions up here. The first thing you want to do is precipitate out the chlorides, right? And those will be silver chloride, mercury, right? Mercury 1, right? Hg2 with a 2+ charge means the charge on each mercury is +1. So we precipitate out the mercury 1 and the lead 2+ with the chloride. Now the advantage to that is we've already added acid to the solution. Now if we add hydrogen sulfide, it's already acidic. So it's already got this added. That adding this is going to keep it over here with just a little bit of that. So now the sulfide, and by the way, this precipitation, this is group 1. The second one, with the added hydrogen sulfide, will precipitate out these. We showed you just copper and mercury 2, but these others will also precipitate with just a tiny amount of sulfide. And then each time you do this, you want to filter your solution so you can extract the precipitates. Okay, so now what you do next? Well, you add a base and you drive it to the right. That makes more sulfide available, and it now reacts with these. Well, you actually get two things going on here. You get sulfides of zinc, nickel, copper, manganese, and iron, but you've also added hydroxide. And that extra hydroxide will simultaneously precipitate aluminum, iron, and chromium. So you get all these in the third group. And then the last one, you add carbonate, right? Sodium carbonate. And what it does is it picks up barium, calcium, and magnesium. All of the, let's see, do we have strontium in there? I don't see strontium. Strontium, if strontium were there, it would come out with these guys, I think. So those are all alkaline earths that come out as the carbonates. And then what do you have left? Well, let's see. I'm not sure what we have left. We have sodium. We have sodium, potassium, and ammonium ions left out of that group. It's color coded. So the first group here comes out first, and then the second one, and then the third one, and then the fourth one. And what you have left over is sodium, potassium, and ammonium. So that's a selective precipitation framework. Now, I don't expect you to memorize this, but I do want you to know how to use the chart. So study the chart and be able to follow the steps, what steps were required to get to each group. Okay. Let me make some room here. Remember when we were talking about silver phosphate? If we added acid, we could increase its solubility because we would remove phosphate and shift the equilibrium to the right. But what about silver chloride? If you add acid, you get no results whatsoever. If you add nitric acid, adding chloride just drives it the other way. So since we can't acidify, or hydroxyls won't do the job either, then we need an alternative way to get this into solution. And that's where the discussion of complex ions comes in. So what is a complex ion? Well, it's kind of like a polyatomic ion. It behaves as a single unit, but it's also soluble. So we take this charged species here and we attach it to various other groups. We call them ligands. Ligands, like, think legs, right? If we got two legs, I have two ligands I'm standing on. But sometimes our compounds will form, our metal ions will form three-legged ligands, or four-legged ligands, or five or six-legged ligands. So what's required? Well, the metal is a Lewis acid because it accepts electrons. So what we need is a Lewis base that will donate the electrons and in the process form a bond that is soluble. So if we can find something that can bond with this silver and go into solution, then it will drive the reaction to the right, right? We need to couple a reaction to this so that we can form a soluble complex ion with silver. That's the next possibility for increasing the solubility of a slightly soluble compound. Here's an example. If we want to put beryllium, some form of beryllium, in solution, then we can form a complex ion with fluoride. Notice, though, that these equilibria are like acid dissociations. They occur one at a time. So beryllium 2+ with one fluoride forms the beryllium fluoride plus ion, the complex ion. And it has a stability constant, or K, of 10 to the 4th. So it goes way to the right. It forms beryllium fluoride. But that one also forms with another fluoride with its own K at 10 to the 3. And then another fluoride at equilibrium 10 to the squared. And then finally, the BF4 2- forms that complex ion with an equilibrium constant of 10 to the 1st power. So these are all favored reactions to the right. That means that they're going to run to the right all the way down until you get BEF4 2-. And the K, overall K for that is 10 to the 12th. So you can form this complex ion with beryllium and the equilibrium shifts it way to the right, forming that complex ion. So if you have a beryllium salt that's insoluble or slightly soluble, this would be a good way to get it into solution. You just make fluoride ions available in large enough concentration so that they will form these complex ions, and you can increase the solubility of beryllium by that. Okay, so now we're going to rehash two strategies for dissolving a water-insoluble ionic solid. If the anion of the solid is a very good base, it's a conjugate, very strong conjugate base, such as this one, aqueous, aqueous, and then phosphate, aqueous. We know that this is a very strong base. If that's the case, then you can increase the solubility of this compound, by simply adding hydrogen ions. Okay? Add hydrogen ions. But if that anion is not a good base, which is the case for this one, right? Chloride ion is a very poor base because it comes from a strong acid. In those cases, you can increase the solubility by forming a stable complex ion with the cation. So in this way, when we add hydrogen ions, we're attacking the equilibrium based upon the anion behavior. But with complex ions, we're attacking solubility with the cation behavior. Oh, I got a video. Okay, so let me get that started.
First, let's calculate the molar solubility of silver chloride in pure water, and then we're going to compare the solubility that we get in part A to the solubility that we're going to get in part B. And in part B, it's no longer pure water. We're going to have some ammonia present. So we take some solid silver chloride, so that's this over here, and we put it in some pure water, and some of the silver chloride is going to dissolve, but most of it's going to stay in the solid form. So silver chloride is only a slightly soluble compound. So there's my little pile of undissolved silver chloride. But some of it does dissolve, and so we get a saturated solution of silver chloride. So there are silver +1 cations in solution, and there are also chloride anions in solution, and we have our solubility equilibrium. To find the molar solubility of silver chloride, let's go ahead and write down our ice table. So our initial concentrations, our change, and finally our equilibrium concentrations. Before we put the silver chloride in, we didn't have any ions in solution. So the initial concentrations of our product are 0, right? We have 0 for the concentration of our ions. Some of the silver chloride that we put in dissolved. So we lost a certain concentration of our silver chloride, and we're going to call that X. So we're losing a certain concentration of our silver chloride. If we look at our mole ratios, for every 1 mole of silver chloride that dissolves, we get 1 mole of silver +1 cations in solution. So for losing X over here, we're gaining X. We're gaining X for the concentration of silver cations in solution. And since our mole ratios are still 1:1, if we dissolve 1 mole of silver chloride, we gain 1 mole of chloride anions. So over here we get a +X. So at equilibrium, our concentration of silver cations is X, and our concentration of chloride anions is X. So we write our equilibrium expression, and since this is a solubility equilibrium, we're going to write KSP, our solubility product constant, is equal to concentration of our product, so that's concentration of Ag plus raised to the power of the coefficient, so raised to the first power, times the concentration of chloride anions, Cl minus, raised to the power of the coefficient to the first power. So we can plug in our solubility product constant at 25 degrees. It's 1.8 times 10 to the -10. So we put in here 1.8 times 10 to the -10. And this is equal to, this would be X times X. So this is equal to X squared. So we can get out the calculator and solve for X. So we have the square root of 1.8 times 10 to the -10. So we take the square root of that, and X is equal to 1.3 times 10 to the -5 if we round that. So X is equal to 1.3 times 10 to the -5 molar. So that's the concentration of, let's say, our silver +1 cations in solution. That's also the molar solubility of silver chloride, right? That's how much we can dissolve. So it's a very small molar solubility. So silver chloride is only a slightly soluble compound. let's see what happens when we have ammonia present instead of pure water. So we have a 3 molar, right? We have some ammonia present now. What happens when ammonia is around silver cations? All right, we get this reaction. So silver cations plus 2 molecules of ammonia give us what's called a complex ion over here. And let's show what's happening. So if we have a silver plus 1 cation, right, we have 2 molecules of ammonia. So let me go ahead and draw in my 2 molecules of ammonia. And this is certainly not drawn to scale. So I'll draw one in on that side. I'll draw another one in on this side. Remember your definitions for Lewis acid, Lewis base, right? A Lewis base is an electron pair donor. And that's what's going to happen here. The nitrogen has a lone pair of electrons, and each ammonia molecule is going to donate a pair of electrons to our silver plus 1 cation. Right, so ammonia is donating as an electron pair donor, so this must be our Lewis base. And the silver plus 1 cation is accepting a pair of electrons, so this must be our Lewis acid. So the formation of a complex ion is a Lewis acid-base reaction. And notice the equilibrium constant for this, 1.6 times 10 to the 7th. Kf is called the formation constant. This is a very high value for the equilibrium constant, right? So the equilibrium lies to the right, and this is a stable complex ion. So any silver ions that are in solution, if you have ammonia present, ammonia is going to pick up that silver ion and essentially remove the silver ions from solution. So if we go back up here and think about our equilibrium, right, if we have ammonia present, we're going to be removing silver cations from solution. Right, so we're decreasing the concentration of silver cations. We're decreasing the concentration of one of our products. And Le Chatelier's principle says if we're decreasing the concentration of one of our products, our equilibrium is going to shift to the right to make more. Therefore, increasing the solubility of silver chloride. More is going to dissolve because the ammonia is present, because of the formation of our complex ion. So if we added some ammonia, right, if we added a solution of ammonia here, we could get our silver chloride to dissolve, right, because it's more soluble because of the formation of a complex ion. So let's say we add enough ammonia solution where we get our silver chloride to dissolve here. So that's the idea. Adding our ammonia, right, caused formation of a complex ion, which increased the solubility of our silver chloride. So we would expect an increased solubility here of our slightly soluble ionic compound, silver chloride. And next, we're going to do the calculation. We're going to find the solubility of silver chloride in our 3 molar ammonia solution. Now we've looked at 2 reactions. We've looked at the solubility equilibrium for our slightly soluble compound, and we've also looked at the formation of our complex ion. Now let's add those 2 reactions together to get our net reaction for what's happening. All right? So we're going to add our 2 reactions together to get a net reaction for what happens when you put silver chloride in ammonia. Right? We have silver cations on our reactant side and on our product side, so we can take those out. And so for our reactants, for our net reaction, we have solid silver chloride plus ammonia. And for our product side, we would have our complex ion and our chloride anion. So we have our complex ion, and we also have chloride anions, so Cl-. So that's the net reaction, and if we added those 2 reactions together to get our net reaction, we have a new equilibrium constant, which I will call K. And if you add 2 reactions together to get your new equilibrium constant, you multiply the equilibrium constants of those 2 reactions. So K is equal to Ksp times Kf. So if you did that calculation, 1.8 times 10 to the negative 10 times 1.6 times 10 to the 7th, you'll get your new equilibrium constant. And I won't do it here just to save some time, but if you do that, you'll get 2.9 times 10 to the negative 3rd. So that's a 9, 2.9. All right, our goal is to find the molar solubility of silver chloride in our ammonia. So we set up our ice table, so our initial concentrations, our change, and then our equilibrium concentrations. And let's pretend like we're starting out with our solution of ammonia and we haven't added any silver chloride yet. So let's go back up here and let's see what our concentration was. Well, we started with a 3 molar solution of ammonia. So let me put that down here. So our initial concentration for ammonia is 3 molar. And if we haven't added any of our silver chloride, then we don't have any of our complex ions. So the concentration, the initial concentration of our complex ion is 0, and we also wouldn't have any of our chloride anion either, so that concentration would be 0 too. So now we add our silver chloride to our solution of ammonia, and some of our silver chloride is going to dissolve, and so we make that concentration X. So we're losing a certain concentration of silver chloride, so we write minus X. Next, we look at our mole ratios. So the mole ratio of solid silver chloride to ammonia is 1 to 2. So for every 1 mole of silver chloride that dissolves, right, we're also going to lose 2 moles of ammonia. So we write minus 2x here. For our products, if 1 mole of silver chloride dissolves, we make 1 mole of our complex ion. Right? So if we're losing X over here, we'd be gaining X over here for the concentration of our complex ion. And same thing for the chloride anion, because our coefficient is a 1. So we're going to gain X for the concentration of chloride anion. So at equilibrium, our concentration of ammonia is 3 minus 2x. Our concentration of complex ion is X, and our concentration of chloride anion is also X. Next, we write our equilibrium expression. So K is equal to concentration of products over reactants. So I look at my complex ion over here, so concentration of our complex ion, and we raise the concentration to the power of the coefficient, so to the first power. This is times the concentration of our chloride anion, so times the concentration of chloride anion raised to the power of the coefficient, so raised to the first power. We also have some reactants here, so we leave silver chloride out because that's a solid, right? But we have ammonia, so this is all over the concentration of our reactant, so this is over the concentration of ammonia. And notice our coefficient is a 2, so we need to have a 2 here. Next, we plug in our equilibrium concentrations. So our equilibrium concentration of ammonia is 3 minus 2x, our equilibrium concentration of complex ion is X, and our equilibrium concentration of chloride anion is X. So on the right side, we would have X to the first power times X to the, let me take that out, times X to the first power. Right, all over 3 minus 2x to the second power, so squared. And then we can plug in our equilibrium constant k, which is 2.9 times 10 to the negative third. So 2.9 times 10 to the negative 3 is equal to, on the right side, we would have x squared. So let me write this out. We would have x squared over 3 minus 2x squared is equal to 2.9 times 10 to the negative third. And so what we could do here, these are both x squared, right? These are both x squared, so we could just say that this is all squared on the right side. And then we could take the square root of both sides, right? So take the square root of 2.9 times 10 to the negative third, and take the square root of what's on the right. So the square root of what's on the right would be x over 3 minus 2x. And let's take out the calculator to do the other one. So square root of 2.9 times 10 to the negative third is equal to, let's round that to 0.054. So it just makes it easier here to round that. So 0.054. Our goal is to solve for x. Our goal is to solve for the molar solubility. So we can multiply both sides by 3 minus 2x. So when we do that, right, we would have this. So we need to multiply 0.054 by 3, and if you round that, you're going to get about 0.16, and 0.054 times 2 is approximately 0.11. So we have 0.16 minus 0.11x is equal to x. So we have 0.16 0.6 is equal to, we put both x's on one side. This is 1x, and this is 0.11x. So 1x plus 0.11x is 1.11x. And so now we need to solve for x. All right, so we've done our math here. So we have 0.16. We need to divide that by 1.11, and that is equal to 0.14. So x is equal to 0.14, which is only approximate because of all the rounding that we've done. So this is concentration, right? So this is our molar solubility. If we go back up here, x equal to 0.14 molar. Right, so that's our concentration of complex ion in solution at equilibrium. That's our molar solubility of silver chloride. Right, so it's 0.14 molar. Let's go way back up to the beginning and compare the molar solubilities. Right, so in pure water, the molar solubility of silver chloride is 1.3 times 10 to the negative 5 molar, which isn't very soluble at all. But now we have ammonia present. We've increased the solubility, and we just calculated the molar solubility is 0.14 molar. And obviously 0.14 molar is a lot larger than 1.3 times 10 to the negative 5. So the formation of a complex ion increased the solubility of our slightly soluble compound, silver chloride.
Okay. So we're going to, let's see, when is our next lab? Next week. Next week, we're going to determine the formation constant for this complex ion, ammonia, and it forms an equilibrium with this one. And that'll be a plus charge. And this is soluble. We want to know what the Kf is, the formation constant. So it would be this one divided by this one times that one. I need two of these. There we go. If we can do this, if we can form this ion, then we can drive this reaction to the right. We can remove that silver from the solution, and it will drive the equilibrium to the right. Notice we've got two ammonias. So this formation of this complex ion occurs in two stages. So there's the equation that we want to influence with the formation of the complex ion. And there's the first step, right? One ammonia combined with a silver ion produces let's see, monoamine silver 1, I think is the way that's named. And there's your equilibrium constant. So it forms way far to the right. That's good. And then it picks up a second ammonia. And that K is also way to the right. So if we write the combined equation, which we're going to do it here. Let's see, is there something relevant here we need to talk about? Virtually all of the silver ion produced from silver chloride is converted to this complex ion. That's good. So as a result, if we composite all three of these, then what do we get? There they are. Silver chloride plus 2 ammonia yields diamine silver 1 and chloride ions. And the K value is, multiply these K's together and you get 2.75 times 10 to the minus 3. So what that means is overall we have increased the K for this reaction. Based upon this reaction, we have increased it by 7 orders of magnitude. So you can get much, much more of the silver chloride in solution. It's not perfect, right? Because it's still 10 to the minus 3, but it's better than 10 to the minus 10. Okay? So the KEQ for this reaction is a simple expression, right? Leave the solid out. This goes in the denominator, and these two go in the numerator. Okay? This explains why the ammonia concentration that we're going to use in our experiment has to be very high. It needs to be high so that we can drive this reaction to the right. Okay, we want the solubility product, the solubility to be high, even though the equilibrium constant is still kind of low. So in order to do that, we have to add lots of ammonia. So we'll add, I think, maybe 1 or 2 molar ammonia, very high, so high you can smell it. And that will increase the solubility of silver to an acceptable level. Okay, so if X is the solubility of silver chloride, this is the following ice table that tracks the change that produces equilibrium. Okay, so here's the overall balanced equation. And we have ammonia here at a certain concentration. Actually, I was way off, 10 molar ammonia. And we have this concentration to start with and this concentration to start with, right? Because at the beginning, we only have solid silver chloride and ammonia. And now we're going to get a reaction. So what does it do? Well, based on the stoichiometry, we get 1 complex ion and 1 chloride ion for every 2 ammonias that are consumed. So if we're going to lose 2, that means 10 minus 2x. We would use S down there for solubility. And an X and an X here. So if we put those values into the equation right here, we can determine the solubility if ammonia is 10 molar. Okay, if it's 10 molar, then we get this expression. Right? And notice, let's see, let me put this on the board. If the KEQ equals like this, like this, like this, over 10 minus 2x, and that's squared. Notice that this is also squared. Right? So if you square the numerator and you square the denominator, you can put a square around the whole expression. That's why we can say x divided by 10 minus 2x squared. Okay, that's nice. That allows us to not have to make an approximation or to use a quadratic. Okay. So whatever the KEQ is 2.75 times 10 to the minus 3. Okay, then we can take the square root of both sides. And that leaves us with x over 10 minus 2x is equal to the square root of 2.7 times 10 minus 3. 7.5 exponent minus 3, and take the square root of that. So that's 5.24 times 10 to the minus 2. Now it's a simple matter of solving for x. We don't have to deal with any quadratics. We can solve for x. And let's see. Oh, we're going to go to town on this one. There we go. And then x is, where is x? Oh, we're not there yet. 0.47 molar. So the solubility in 10 molar ammonia, the solubility now is equal to 0.47 molar, which is huge compared to our original calculation. What was it, 10 to the minus 5? 1.3 times 10 to the minus 5? Right? That's a huge improvement in solubility, simply by adding ammonia. Now, what this does is tell you, all right, how much ammonia is left that's not complexed. And that's what this one does. Right? We take the expression over here, 10 minus 2x, right? That's what's left at equilibrium. So 10 minus 2 times 0.47 is 9.06 molar. So we've only used up 1 molar concentration of our ammonia, and we left 10.06 molar behind, uncomplexed. Oh, that's it. That's the last slide. Let's see how we're doing on time. We got lots of time. Maybe we've got time to talk about the lab.